Dear students, in the last class we have discussed about the concept of load line and operating point and also concluded that the best location of the operating point should be at the center of the load line. Now in this class, let me discuss the stabilization of the operating point Q. And as usual, let us take the output characteristics of the common emitter configuration VCE versus IC, keeping the input current, base current as constant. And you know the basic equation VCE is equal to VCC minus ICRC. By taking the x coordinate and y coordinate here, you got the two extreme points here. One is VCC and other one is ICRC. So these are the VCC by RC. So if you combine these 2 points here, and this is nothing but the load line, the intersection of the load line with the characteristics is nothing but your operating point Q. Operating point Q, you are having a coordinates of VCE and IC. The best location of the operating point is at the center of the load line. Now it is at the center. But we have to keep always the operating point to be at that center only. But the operating point Q always changes, because here the operating point Q having the coordinates VC and IC is always not constant. IC is a function of temperature. If temperature changes, IC changes. If IC changes, operating point Q also changes. That thing I can explain you using the mathematical equations. You know, IC is equal to beta times IB plus ICEO. ICEO. Beta times IB plus ICEO. ICEO means reverse saturation current in common emitter configuration. So this can be written as IC is equal to beta times IB plus beta plus 1 times ICBO. ICBO means the reverse saturation current in common base configuration. The last classes I told you here, the reverse saturation current in common base configuration is less compared to the common emitter configuration. In the common emitter configuration, the reverse saturation current is more. How much it is more? Beta plus 1 times more. So this is the basic equation for your IC. Clearly this equation is telling it is not only depending on IB, it also depends on your beta, it depends on your reverse saturation current also. So reverse saturation current ICBO is nothing but reverse saturation current is a function of temperature. Just like it is diodes, here also it is a temperature dependence. And your collector current also depends on your beta. Beta means it is a gain of a transistor. Whenever a transistor has damaged, you have to replace with another transistor. Whenever you are having another transistor, its beta will be different. So from unit to unit, the beta changes. So whenever you are replacing the equipment, you are replacing your transistor with another transistor, beta should not be the same. Because of the lack of techniques in your manufacturing technology, beta always changes from transistor to transistors. That's why I can tell you, no two transistors will be having same set of characteristics. That's the most important point you have to note down. So your collector current is depending on both beta as well as your reverse saturation current. The dependence of this IC on this reverse saturation current is nothing but the concept of your thermal runway. Thermal runway I can explain you. Suppose if temperature changes, T changes, that means T increases. Your reverse saturation current ICBO also increases. If ICBO increases, ICEO also increases. So you can say ICEO increases. If ICEO increases, naturally IC increases. IC means collector current. Collector current is flowing across your collector junction. If IC increases, the temperature at the collector junction also increases. So once again temperature increases. If temperature increases, ICBO increases. And if ICBO increases, ICEO increases. ICEO increases. If ICEO increases, once again IC increases. And if IC increases, temperature increases. So it is a cumulative process. It is a cumulative process takes place. So as it is having this cumulative process, then after some time, as the maximum collector current is flowing across the collector junction, there is a destruction of a transistor. It is indirectly, I can say, it is a self-destruction of a transistor. Self-destruction of a transistor is called as thermal runaway. Thermal runaway. So, naturally in your airports you can have a runway. Runway means it's a long route. Exactly here also it is a cumulative process. Temperature increases, reverse saturation current increases, ICU increases, IC increases, once again T increases. Like that the process continues. After some time the transistor is going to be damaged. That's the reason it is called as thermal runaway. So, to avoid this, of course, we are going to have some techniques. Those techniques we are going to discuss in detail. And now, once you know this thermal runaway, then I can understand that your IC is a function of both beta as well as the temperature. Now, to compensate this variations against beta and this temperature, we have to use some biasing techniques as well as the compensation techniques. So, I hope I understood clearly. Q is a function of VC and IC. IC is a function of temperature. If IC changes, operating point also changes. If operating point position changes, if it is traveling towards your either saturation region or cutoff region, faithful amplification is not achieved. For getting the faithful amplification, our duty is to see that IC should not change with temperature. So, for that, now we are going to discuss some techniques. Those techniques are nothing but your biasing techniques and compensation techniques. Now, let me discuss the biasing techniques in this class to fix up the operating point. Okay. To fix up the operating point Q, we are having different types of biasing techniques. One is the fixed bias, and second one is collector to base bias, third one is self bias. So, let me discuss in detail what is fixed bias here. You know very well, operating point means Q having the coordinates of VCE and IC. And you have to find out what are the values of IC and VCE for every biasing technique. For this very simple, my dear friends, to calculate your IC and VCE, you have to apply the Kirchhoff's voltage law for the input loop as well as for the output loop. So, let me tell you clearly. Let us take this fixed bias circuit. Here, the transistor is in which configuration? Common emitter configuration. You are taking the output at the collector, V0, that is nothing but VCE. And here this is RC, current is IC, RB is a base resistance, the current through this one is IB. The voltage existing between the base and emitter is plus VBE. Now, let me write the KVL for the input loop. So, KVL for input loop. If you write the KVL for the input loop, your applied voltage is VCC. VCC is equal to IBRB plus VBE. So, you are coming for this loop. This is the loop. VCC is equal to IBRB plus VBE. Your applied voltage VCC is equal to IBRB plus VBE. What is VBE? VBE means base to emitter voltage. It is a diode drop. It is a diode because input junction is nothing but a diode. The diode drop may change with some material. It is your VBE drop will be your 0.3 for your germanium and 0.6 or 7 for silicon. This is nothing but the VBE. So, sometimes you can neglect it also, otherwise you can consider it. Now, if you write here VCC is equal to IBRB plus VBE, I want to write what is IB here. So, IBRB is equal to VCC minus VBE. Then what is IB here? IB is equal to VCC minus VBE divided by RB. This is the base current IB. But remember here friends, here the VCC is fixed. Whatever the supply are giving is nothing but the VCC. It is fixed. VBE, it is 0.6 for silicon and 0.3 for germanium. It is also fixed. RB, base resistance is also fixed because you have given the base resistance. If all are fixed here, your IB is also fixed. That is the reason it is called as fixed bias circuit. The reason for calling it is a fixed bias because all parameters are fixed here. If IB is fixed here, your IC you can calculate using the expression IC is equal to beta times IB. And remember, always in the biasing circuits, from the input loop we are going to calculate IC. IC is nothing but the coordinate of the operating point. Exactly like this, you can calculate your VCE from the output loop. The technique is very simple, friends. Just write the KVL for the input loop and output loop. From the input loop, you are going to calculate IC after calculating IB. And from the output loop, you are calculating VCE. How to write down the KVL for this output loop? VCC is equal to applied voltage is equal to ICRC plus VCE. So I can say for the output loop, KVL for the output loop, VCC is equal to ICRC plus VCE. Therefore, VCE is equal to VCC minus ICRC. So, IC is already given from the input loop. Just now you calculated IC is equal to beta times IB. IC is available, VCC is available, RC is available. Happily you can calculate what is VCE. Then that means nothing but your operating point Q. So, Q of VCE into IC. So, I told you very clearly why it is called fixed bias circuit and how to calculate your IC as well as VCE. Once your operating point is actually calculated here, it is excellent. But fixing the operating point is not sufficient. We have to see that whether the Q changes with the temperature or beta. Every biasing circuit after designing, you have to see whether the operating point is Q is stable or not. So, first of all, let me check with the temperature variations. So, for every biasing circuit, you have to check the temperature variations. First one, temperature variations. Temperature variation. Already you know very well, your operating point is fixed. Temperature, how it is. Now, in this circuit, now if the temperature increases, okay, temperature increases, ICB also increases and ICEO also increases, then automatically your IC also increases. If IC increases, then once again temperature increases. If temperature increases, the cumulative process takes place. That means the self-destruction of the transistor takes place, which is nothing but a thermal runaway. Thermal runaway means self-destruction of the transistor. So, temperature variation is failure. There is no question of taking care of these temperature variations. The very first point actually fixing Q, fixing of operating point Q is good. We have fixed it. But whereas the second point temperature variation is a failure. And the third one is beta variations. So, what about the beta variations? Beta variations is also failure because IC is equal to beta times IB. IC is equal to beta times IB here. IC is changing. If beta changes, IC also changes. So, that is the reason fixed bias circuit is not a famous circuit. So many times the people are not using this fixed bias. Of course, the advantages are very simple. It is a very simple circuit, simple to design and low cost and very easy to maintain this. But only the problem is it is not taking care of temperature variation and beta variation. So that is the reason. So fixing the operating point is excellent. Temperature variation is failure and beta variation is also failure. That's the reason this fixed bias circuit is not a famous circuit. And that's the reason we are going for the next biasing circuit, that is called collector to base bias. Just now we have discussed about the fixed bias circuit. In the fixed bias circuit, the problem is we have not taken care of the temperature variations and beta variations. Let us see what happens in the next biasing technique, collector to base bias. So, if you see this circuit, it is a fixed bias circuit. Now, just I am changing this fixed bias circuit into collector to base bias. So, the name itself is telling it is collector to base bias. This is a collector terminal and this is the base terminal. In between, we are going to use this resistor. So, just you disconnect this resistor RB and put this resistor between the collector and base like this. This is RB. As soon as you are changing the resistance like this, so this is the base current IB and this is the collector current IC, then definitely the sum of the two currents will be here, IB plus IC. So this current will be now IB plus IC. As you are connecting this collector and base with a resistor, it is called as a collector to base bias. As usual, for calculating the operating point Q, you have to write the KVL for the input loop as well as for the output loop. So, how to write the KVL for the input loop? For input loop you can say the applied voltage VCC is equal to this drop plus VBE. So, VCC is equal to IB plus IC into RC plus IB RB plus VBE. VBE is a diode voltage drop as usual. So, from this I would like to write down what is IB. So, VCC minus VBE is equal to, here IB RC, IB RB. I can take IB as common, IB into RB plus RC plus IC RC. This is IC RC. Now I can write down here IB is equal to VCC minus VBE minus ICRC divided by RB plus RC. So here you see, what do you mean by VCC minus VBE, okay, minus ICRC. VCC minus ICRC is nothing but the output voltage. So this can be written as VCE minus VBE divided by RB plus RC. So this is the input current expression IB. Once you get this IB, very easy to calculate your IC. IC is equal to beta times IB. Therefore, you can write down here IC is equal to beta times IB. So from the input loop we have calculated IC. What is the coordinates of the operating point? What are the coordinates? Q is having the coordinates of VCE as well as IC. Already IC has given from the input loop. As usual, from the output loop you can calculate for your VCE. From output loop, just by writing your KVL, output loop, you can write the KVL here. VCC is equal to ICRC plus VCE. So you can say applied voltage VCC is equal to IB plus IC into RC, this is the drop, plus VCE. I can say if you compare IB and IC, IB is in terms of microamperes, IC will be in terms of milliamperes. IB is very less than IC, so you can neglect it also. So I can say your VCE is equal to ICRC plus VCE. So from this you can calculate your VCE. VCC is equal to. So VCE is equal to, then you can say that VCC minus ICRC. So this is the way of calculating your VCE. So very simple. Just by taking the circuit, we have calculated both IC as well as VCE. That means operating point is fixed. Once operating point is fixed, our duty is to check whether the operating point is changing with your temperature or beta. So now let me check whether they are changing it or not. So if you are taking these variations here, for the fixed bias, fixing the operating point is excellent. We have fixed it. And the temperature variation is a failure. Beta variation is also failure. Now let me check for this circuit, collector to base bias. In the collector to base bias, what happens? If temperature increases, ICBO increases, then ICEO increases, then IC increases, Listen carefully, IC increases, So this is the cumulative process. Temperature increases, ICBO increases, ICEO increases, and IC also increases. Now let us take this circuit for the input loop. From the input loop you see, if IC increases, here, then VCC minus ICRC decreases. If the collector current increases here, then your output voltage VC is equal to VCC minus RC decreases. IC increases means the numerator decreases. If the numerator decreases, your IB decreases. So indirectly, the raise in the collector current actually decreasing the input current now. If IC increases, your VCC minus IC also decreases. That means output voltage decreases. So if you see this, what is VCE? VCC minus ICRC. So VCE decreases. VCE decreases means IB decreases. So that's why I can write here, if IC increases, then IB decreases. IB decreases. If IB decreases, then once again there is a control. If IB decreases, input current decreases means then definitely your IC decreases. This is the action that is taking place. So once again I repeat, if temperature increases, reverse saturation current increases, collector current increases. If collector current increases, from the input loop equation IB decreases. If IB decreases, once again IC will be in control. That means for the collector to base bias CB, fixing the operating point is excellent, we have fixed it. And the temperature variations also excellent. Temperature variations also you have taken care of. But what about the beta variations? Beta variations also, if you are taking this equation, IC is equal to beta times IB. If the transistor changes, beta also changes. If beta changes, IC changes. If IC changes, if IC increases, let me say, then automatically IB is decreasing according to that equation. Because that equation is nothing but IB is equal to VCE minus VBE divided by RB plus RC. This is the equation, basic equation. If IC increases, VCE decreases because VCE is equal to VCC minus ICRC. So if IC increases, VCE decreases. If VCE decreases, IB decreases. IB means input current decreases, means IC will be in control. So this is also taken care of. Even the beta changes, there is no question of any changes in the operating point. So the third point is also excellent. So if you compare with your fixed bias and collector to base bias, in fixed bias, first point is satisfied. Another 2 points are failure. Whereas for the collector to base bias, all the points are excellent. We have fixed the operating point, temperature variations are also not there, beta variations are also not there, but still the people are not using the circuit. Why? The reason is very simple. Just observe this circuit once again for the disadvantage. Advantage is fixing the operating point, it is taking care of the temperature variations, it is taking care of the beta variations, but only the disadvantage is the gain will be reduced in this circuit. So once again, friends, please concentrate here. If you are taking this collector to base bias, this is the output point here, this is the output point here, and this is nothing but the input point. One resistor is connected between this output and input. So whatever the output here, some fraction of the output is actually feeding to this input. Actually we want more output here, but a portion, a fraction of this output is feeding to this input here. So net output is actually decreasing. Net output is decreasing. Suppose if you are manufacturing some goods here, 100 goods you are manufacturing. Out of this 100, 5 to 10 goods are actually having a problem. Once again, you are throwing back. That means net output decreases here. Exactly because of this feedback resistor, some voltage is feeding back from output to this input. So that's why it is called as voltage feedback is taking place. That's why the gain is reduced. So what is the disadvantage? It is a voltage feedback circuit. So some portion of the voltage is actually feeding from output to the input. So the net output decreases, indirectly the gain decreases. What is gain? Gain means output voltage by input voltage. If this resistor is not there, then the gain will be more. but if it is not there, means there is no question of biasing. That's why there should be a compromising value. So because of this disadvantage, the people are not using this collector to base bias also. That's why everybody is going for the next alternative, which is the most famous biasing technique, that is called as self bias, emitter bias, or voltage divider bias, and that thing we are going to discuss in the next class. Okay, thank you.